In this video, we are going to discuss Theorem 11, Limit Comparison Test. This is the second test in topic 11.4. Let me explain first what you meant by the Theorem 11. In using the limit comparison test to check for the convergence of a series AN with all the terms in the series non-negative, you are supposed to propose a series Bn, and you use the series Bn to calculate the limit of the ratio of AN over Bn for n tends to infinity. By knowing the limit of this ratio and the convergence properties of the series Bn, you will be then able to say something about the convergence or divergence of the series An. There are three possible scenarios. Let us look at the first extreme situation where the ratio is infinity. The limit of an over bn tends towards infinity when n tends to very large. It somehow gives you a picture that the an is always much larger than the corresponding term in the series of bn. If you further know that the series of bn is diverging, then this will infer the series of an is diverging. The other scenario is the opposite extreme where the ratio is equals to 0. In that case, it somehow gives you the picture that an is much smaller than bn when n is tending towards very large. And if further you know that the series of bn is convergent, that would imply the series an is convergent. You can take this scenario as represented by an larger than the bn when n is very large. In this picture, you see the bn series is lying below the an. So that gives you an intuitive feeling that should the series bn diverges, then the an which is sitting above bn should also diverge. For the scenario where the limit goes to 0, it gives you this picture. The series of an is smaller than the series of bn in the limit n goes to very large. So intuitively, if bn is converging, then the series an which is lying below the series bn should also converge. The third scenario is an intermediate scenario where the limit of the ratio an over bn tends towards some number c, which is neither 0 or infinity, but a finite positive number. For such a situation, then the series an and bn will both converge or both diverge. In other words, it means if the bn is a converging series, so will be the an series. On another hand, if the bn is a diverging series, then it infers that the a series is also diverging. The easiest way to understand the limit comparison test is to look at the example. In example 2a, we are dealing with a series an which is expressed as 2n plus 1 over n plus 1 squared. So how are you going to propose a series bn that will be used to compare with the series an? In the case of the limit comparison test, the propositions of the form of bn is much easier than the comparison test. In the case of a direct comparison test, you have to create your own bn for comparison with an. In the case of the limit comparison test, you can propose the expression for the bn by looking at the expression of an itself. Here is how we do it. You look at the expression of an and try to figure out what would be the behaviors of an when n is extremely large. If n is extremely large, then the expressions of 2n plus 1 over n plus 1 square would be reduced to 2n over n square, where the term 1 in 2n plus 1 will be roughly dominated by the term 2n, whereas the n plus 1 term in the denominator will be roughly dominated by the n term. So it's quite trivial to see how an behaves when n is taken to be very large. In that limit, you just drop the 1 in comparison to the 2n in the numerator and n in the denominator. The series Bn can then be taken to be the form of an when n is becoming very large. In other words, in this case, we will take Bn to be equals to 2n over n squared, or simply 2 over n. So here is the suggested series of B to be made comparison with an. We then proceed to write down the limit of an over Bn when n goes to infinity. This will be just equals to the limit of n goes to infinity for an divided by Bn. An is 2n plus 1 over n plus 1 squared. Bn is 2 over n. The limit could be easily obtained. What you do is you pull out the factor of n from the denominator and the numerator. Here in the numerator, I pull out the factor of n from 2n plus 1. So what is left in the factor of 2n plus 1 become 2 plus 1 over n. In the denominator, I'll pull out the factor of n. I'll have n squared of 1 plus 1 over n with a square. So the n squared in the numerator and the denominator get cancelled off, and the term of 1 over n will get to infinity when n gets to very large. So we can drop these terms, and what is left at the end is just equals to 1. So we come to the conclusion that the limit of an over bn when n goes to infinity is a finite number of 1, which is neither 0 or infinity. Therefore, it means both series an and bn would be either both converge or both diverge. So now we look at the series of bn and check the convergence of the bn. Convergence of Bn is easily concluded because the Bn is nothing but just the harmonic series. And we know the harmonic series is divergent. Therefore, the series Bn is divergent as well. Therefore, by the virtue of the limit comparison test, An is divergent too, because Bn is divergent. Now let us look at example 2b. In example 2b, the series to be tested for its convergence is in the form of an equals to 1 over 2 power n minus 1. We would like to first obtain the suggested series Bn by taking n in an to a very large number. We can see from the expression of an that when n is very large, then an would behave like 1 over 2 power n. With this, we then suggest the series Bn to take the form of 1 over 2 power n. Limit of an over bn and take n goes to infinity. The expression for an is 1 over 2 power n minus 1, whereas the expression for bn is 1 over 2 power n. So this is the expression for the ratio of an over bn. I must not forget to slot in limit of n goes to infinity. So now I have to look at the limit of this ratio when n goes to infinity. And it is quite obvious that this limit will tend towards 1 because when n become very large, 2n minus 1 will just drops to 2 power n. Therefore, the numerator and the denominator get cancelled off and give you the factor of 1. Therefore, again, in this example, we have a situation where the limit of an over bn tends towards an finite values of 1. Therefore, it means the fate of series of an and the series of bn are tied together. Namely, both will either converge or both diverge. Therefore, to tell whether the series of an is convergent or divergent, we just simply need to look at the convergence of the series Bn. The convergence of series of Bn is easily determined because we know this is just a geometric series with a ratio of half. Therefore, the series of Bn is convergent. By the virtue of the limit comparison test, this will also imply that the series of An is also convergent. So that completes the calculations of example 2a and 2b. To conclude, in the limit comparison test, where you are to determine the convergence of a series an with all the term an non-negative, you first try to see what is the behavior of the an when n is taken to be very large. Then whatever resultant expressions that you arrive at will suggest the expressions of the series Bn. Once you have obtained the form of the series Bn, you can then proceed to calculate the ratio of An over Bn when n tends towards infinity. By looking at the result of the limit and combine it with the knowledge of the convergence properties of the series Bn, you can then conclude whether the series An is convergent or divergent. In both cases that we have shown in example 2a and 2b, the limit of both examples are shown to be finite. Therefore, in both examples, the fate of series A and series B are tied together. With that, we can then conclude the convergence of series A because we know the convergence of the series B.